Okay. Can you guys hear me? Oh, wow. That is quite loud. All right. Great. So a little bit of intro into me and what I'm up to. I work for a company called Numerical Research in Stellenbosch. We're basically managing a bunch of investment funds using machine learning algorithms. There is no human involvement apart from actually developing the algorithms. And we've been doing that for about 3 years now. And it's been a very interesting experience because I think that financial markets are probably about as hard as it gets in terms of predicting things. They're very noisy and your accuracies are way lower than what you see on image recognition tasks generally. Can we just close the door? Thanks. So my role at Numerical Research is I'm now the chief scientist, used to be chief engineer, but now that's changed because we've hired a guy who is much better at scaling than I am, which is cool because it lets me focus on all the cool tricks and new models and new algorithms, which is really what I love. My background is computer science, studied at Tux. I don't think too many people here are from Tux, but there's a great research group there called CIRG, Computational Intelligence Research Group. So I was a part of that, dropped out of that. Not very academic myself. Actually enrolled in another master's and dropped out of that one as well. So it hasn't been going well on the studies front, but we've been doing cool shit, so I'm happy about that. We've developed a framework which is really just a general purpose multivariate time series prediction system. It's got hundreds of different classes of machine learning algorithms implemented. And today what I'm going to basically be talking to you about is just a bunch of tricks for doing deep learning in complex dynamical systems, because machine learning is really nothing more than a bag of tricks and you pull one out and you try and see if it works. This is what our textbooks told us the world was like. It lied. It's not like that at all. You have your training set and your test set and you build your model and you think that it's just going to work perfectly in the real world, but the real world doesn't care about your models, and this is typically what happens. So the world changes and your model is in production and everything just breaks and you see things happening that theoretically shouldn't even be possible. So there are a few names. There are a few names for this. It depends on who you talk to. Concept drift is the machine learning name. So this is where basically the distribution of input and output patterns actually shifts and changes over time. If you're talking to guys from statistics and maybe biology, they'll call it a regime change, and these occur very often in ecosystems and habitats. And if you're talking to the physicists, it's a phase transition. So maybe you have like some sort of magnetic system and then the polarity kind of changes. So you see these dynamical systems in the real world all over the place, and financial markets is one of them. So most machine learning methods make one assumption, and that is that the data generating process is stationary. So basically, we are trying to learn a function which maps inputs to outputs, and we kind of assume that that function doesn't change over time. More often than not, this is actually an unsound assumption. So in dynamical systems, it's naturally unsound, but even in things which should be stationary, often you find that this assumption is violated. So one of the classic examples, and it really comes more from optimal control, so you've got some factory and you're trying to manage your machines, but it also applies equally to self-driving cars, is this idea of like sensor degradation. So let's say I buy a really nice self-driving car, not from Uber, but from somebody who doesn't kill people with them. And at first it works 100%. The images that it gets from the cameras and LiDAR and everything is pretty much within the distribution of how the models were trained, and I don't die. So that works really well. But then let's skip like 7 years into the future. I mean, many of us are probably driving 7-10-year-old cars. How are those sensors going to be performing 7 or 10 years in the future? What happens if they just get old? You have a change in the distribution of your patterns. So you actually need to identify those changes and implement and update your models. Or what happens if you still have a new car and you just had a minor bumper bashing and you took it into the shop and they fixed the bonnet, but did they go and check all the electronics and make sure that your sensors and your LiDARs are actually calibrated correctly and you're not going to die next time you drive your car? So I mean, in the real world, there is concept drift, so this is an example of concept drift. But what we're more interested in numerical research is actually true dynamical systems. So you get a few different types of dynamical systems. You get ones which are stochastic, so there's just a lot of randomness involved. I would say that markets are probably in that category, as well as the second category, which is adaptive. So where your system is actually changing through time. So a market is really nothing more than a capital-weighted consensus mechanism. Whatever people think is going to happen, if those people have a lot of money and they trade a lot, that is what happens. It's really as simple as that. Another type of dynamical system is one which is sensitive to initial conditions. So this is weather, for example. You need to have a 100% precise measurement of your state in order to predict what is going to happen going into the future. More often than not, you cannot get precise measurements. In the case of weather, I mean, it comes down to like basic physics. But in financial markets, generally the state is intractable, so you can't even try to measure it. So I'm going to talk about 3 classes of tricks which can basically help you to solve this problem, because I'm not very interested in standing up here and telling you guys, oh no, it doesn't work, most of our assumptions that we make are false. I'm interested in telling you how we can actually solve this problem. So the 3 classes of tricks I'm going to talk about is first data sampling. So that's how do you pick the data that you train your model on through time. And then data augmentation, which is how important or how should you weight the data which you're training on through time. And then the third one is model augmentation. So can we take our models, our deep learning models, and can we augment them in such a way to actually make them better at this problem? So just quick diagram of like what a non-stationary environment might look like. These are 3 probability distributions, and you can see that basically it's changing through time. At time t, we've got some nice bell curve. Well, we have nice bell curves at each point, but they have different means and variances. So it's kind of shifting over time. So the first talk in this session was talking about how you might train a model to detect or deal with I think it was traffic on a network. This is an example of like a time series prediction problem. So the approach which was presented in that talk, and which is kind of like the initial approach, is to really do supervised deep learning through time. And this really is, you have data and it's coming into your model, and what you do is you select some window of that data, and from that window you get your training input patterns and your training responses, your validation patterns, your validation responses. You build your model on the training data, you test it on the validation data, and then you use that going forward. So there are 2 commonly used techniques here, and one is to use basically a fixed window size, and one is to use an increasing window size. So I put a little red dot on the time axis, that's the white line at the bottom, to indicate where a regime change or phase transition or some change in the distribution kind of occurs. So as you can see, when we're using a fixed window size, we're actually quite pessimistic in how we sample data, because we could have used window 2, which is that blue curly bracket over there, and most of window 1 to train our model at the end of the time point, but we end up only using a little bit of data. Now the impact of that is naturally that you have less data to train on, right? So if you have less data to train on, you cannot train very complex models. It's also just inefficient, because there might be patterns which are seen in the early stage of window 1 during that phase transition, which you might see again, and now you haven't seen it in your training process because you sampled your data in an inefficient way. So Similarly, what we could do is we could just increase the window size. So we say, all right, well, we're moving forward in time. We're just going to use as much data as we have available to us. Now, this is very optimistic in data sampling, especially if you're in a non-stationary or complex dynamical system, because you end up using data which might be completely irrelevant to the task at hand, because in dynamical systems, the task actually changes. So the function which you're trying to learn needs to change through time with that. So the benefit of this is that you get more data, which means you can train more complex models. It obviously means that it's slower because now you have more data. But the problem is that you could end up in a situation where most of that data is irrelevant. So an example from financial markets is what drives stock market prices in 2007, just before a financial crash, and what drives them in 2010 after we've gone through like a bottoming out and everything is cheap is fundamentally different. And the reason why it's fundamentally different is because the people who are invested in the market at that point, or the people who have the most capital in the market at that point, have changed. The guys who were sitting on cash in 2007 now have the most money in 2010, so what they think influences the market more. So it literally has adapted, has changed. So I would hardly call this a trick. It should be standard practice. But I mean, the easiest way that you can solve this problem is just ensembling. So what we're going to do is we're going to train two models, and we are going to ensemble them together. And the idea here is that the best model is going to be the one which is trained on the most relevant data. And we're measuring best in terms of out of sample. So we train on data up to time t. We're going to measure our performance from time t+1 onwards. And we're going to weight according to that information, so the predictions coming out of the models. So how that might look is we have a fixed window size model at the top. We have an increasing window size at the bottom. We are getting our inputs and our outputs at each window through time, feeding it into two different models, and then we are combining them with an ensemble. So there are a few different ways that you can do this. You can use you can just use a voting system where your best model gets the highest vote in what it thinks the prediction is going to be. You can also do stacking. So what you can do is you can pull out the voting system and you can put in another neural network there. And then the job of your ensemble neural network is really just to learn what predictions from what model to use at what point in time. And it's important that that is continuously changing through time as well, because in this situation, you might find that increasing window size works well almost all of the time, except for periods where you have regime changes or phase transitions, in which case you might actually want to use a very pessimistic data sampling technique, because only the most recent data is relevant. In financial markets, if you're going through a financial crash, maybe only the last 30 days is relevant. So 30 days worth of data is nothing. I mean, you can train a model on 3 or 4 years worth of data. Most of the time it'll work, except for when you really need it to work. Yeah, that's my life, is looking at these things, yeah. Another one which I'm quite a fan of, I think this is cool, is actually implementing change detection and hypothesis testing. So I just want to jump back to this slide over here and point something out. This one. So we have our data, which is this white, nice line, which is just going up and down. And we have this red line, which is really the predictions from our model. And you can kind of think of a model as building up an internal representation of some system. So it's learned how this market or ecosystem or whatever should behave through time. And what happens when that belief breaks down, so the market actually changes, things shift, is that you see an increase in error. So that bottom graph over there really just shows an increase in the error terms of your predictions. Now, obviously, that's lagged by however long your predictions are, but it is an interesting metric to determine when phase transitions actually happen. So the idea over here, change detection and hypothesis tests, is actually to monitor the error terms of your model and use its uncertainty or its error terms as an indication of a change having occurred. And at that point in time, what you can do is you can either change your window size or you can adapt your model. There are a number of different strategies which we're going to talk about. So how does that look? We have our neural network, we're training it through time, we're training it on an increasing window size, but from the previously detected change point. So in this situation, what we're doing is we're continuously monitoring some variable epsilon, which corresponds to the error term or the mistakes that our machine learning model has made. And when that crosses some theoretical boundary, then we reset our window. So we start with a very pessimistic window, and we allow it to grow until the next change occurs. So there are a few different ways that you can do that. If we're talking about change detection tests, these are normally done on a cumulative random variable, and what we do is we estimate some threshold for this value, and if it crosses that threshold, then we say, we're in a totally different regime, let's reset our window sizes. So there are a few ways that you can do that. There's something called hoof thing that bounds. I'm not sure if I'm saying that right. Hellinger distance, pullback lever, divergence. There are a whole bunch of different measures of similarity across distributions that can be used. One of the most popular technique here is actually called the Q-sum test, which we've got in our framework. We're testing it out. That's quite different to a hypothesis test, though. So what you do in that situation is, all you do is at every point in time, you increase your window size, you split it in half, and you say, is the distribution of the first half the same as the second half? And you basically grow the size of your window up to the point where statistically you're not confident that the distributions are the same anymore. So you can use a Kolmogorov-Smirnov test to do that. So basically you just increase your window size until the distributions actually look statistically significantly different, and then cut from there. Yeah. Yes. Oh yeah. So the window, the window size. So at the bottom we can see these curly brackets show how big the window is. What we do is we reset the window at this point, and we start counting up from 1. So maybe we say that the window size now at this point in time is actually 0 because we have no relevant data to train on. So then, what we might do is we might say, all right, don't use your model for the next 30 days, build up at least 30 days worth of data, and then that's your new window size. Yeah. So it's really just trying to work out how much data we have which is actually relevant to the task at hand. Yes. Yeah, it does. Yeah. 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 So that's one of the tricks we're going to talk about just now. I've got a whole bunch of tricks. This is probably the most sound trick. Yeah. 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 No, this guy gets it. Yeah. No, we do try different things, and we try to use the ones which are most likely to succeed and other people have written about and published. These are not things that we just make up. There are actually a lot of papers written about using change detection tests in optimal control settings, which I'll happily send to anybody who emails me afterwards. Yeah. So that's an interesting question. With deep learning, one of the problems is interpretability. So we use our deep learning models to identify when a regime change has occurred, but we don't know what that regime change is. In fact, we don't even know what's going to happen next. You could go from a regime where you're in a bull market to a regime where you're in a flat market. Or maybe, and this has happened once in our historical simulations, the regime change occurs because what your model thinks is going to happen is not quite as optimistic as what actually happens. So if the market goes up way more than your model expects, that's technically a regime change as well. So it's very interesting to kind of come back and say, well, what do we expect to happen next? What actually was this regime change? So a lot of the research we're doing now is on actually interpreting that kind of stuff. But no, we don't say what happened, we just say something happened. Correct. Yeah. To some extent. The last trick, which I'm going to talk about, is actually how we can maybe predict. So we're not basing it on a lagged error term. We're actually basing it on model uncertainty, which ties back to the previous talk. I'm actually going to show how you can use a neural network to kind of get a distribution of uncertainty. Yeah. So the next technique is time series subsequence clustering. We spoke about this a little bit earlier. There's very mixed reviews on this in academia. So there are some papers like, for example, time series clustering is meaningless. That is the title of the paper. So this is like, maybe a little bit of a gray area. But the idea is quite simple, and that's really that we can assume, or what we do is we take our amount of time that we have, and we reformulate that as really an unsupervised classification problem. So what we want to do is we want to say, well, what periods historically kind of look similar to this? Because maybe what we're doing is we're shifting from one regime into a new regime, but we've actually seen that regime before. So classic example in financial markets, if we go from 2007 through 2008, we're going through a regime change, which is a market crash. 2001 is another example of a market crash. So maybe what we should be doing is sampling data from 2001 and training our model on that so that we can react very, very quickly and we don't have to wait until we have a statistically significant sample size. So how that looks, very simply, is that at each point in time, what we're going to do is we're going to encode our subsequence of time, and we're going to cluster it. So we're going to basically break it up into different possible regimes, and there are different ways that you can do this, and then we're going to estimate what our regime is right now based on the most recent data patterns, and we're going to sample from that. And the cool thing about this is that it's not optimistic or pessimistic if your clustering algorithm is correct. And you don't need to sample data contiguously, right? So contiguously means you're sampling data next to each other through time, which is kind of what most time series analysis involves. What we're doing here is we're just saying, well, let's work out what data from here looks similar, and that could be similar from a distributional perspective or from like literally a distance metric perspective, and we're sampling data from there. So over here, we've classified this as a dog cluster, and all we're doing is we're just sampling from wherever we saw that in the past. So maybe 2008, we're sampling from 2001, 1967, all the previous kind of like stock market crashes. It's very computationally expensive and difficult to implement because now you've got an entirely new algorithm. You've got your clustering algorithm, which you've kind of built in here, and this technique only works if that model works. And what you don't want to end up with is, let's say you have some distribution of patterns, and what you end up doing is saying that everything at the end of this distribution is in the same cluster, and everything from this end of the distribution is the same cluster, but actually they're all part of the same regime. So the choice of distance metric when you're doing this is very important. And it's also very sensitive, because if you cluster your data and you leave some stuff out completely, then your model has no opportunity to learn from that. So if you see that next, then your model has never seen anything like that before, and it will fail spectacularly. We're going to talk a little bit about how. Sorry, some questions.
So what do you do with the variations of the time series or the different sources of time series during this clustering?
Different types of time series.
Yes, but so all those different variations in the time series.
Yes.
In the clustering.
So, I mean, the technique I'm quite a fan of is actually using distributional tests in this case. So what we're going to do is we're going to basically break this up into a whole bunch of subsequences, and we're going to do a whole bunch of statistical tests. So we're going to test if this subsequence is likely to belong to the same distribution as this subsequence. Yeah. So that is a good question. You should probably, well, how we do it is we say, well, what is the minimum amount of data we need to actually run this test? So if you're running a statistical test, maybe you need, 30, 40 data points at minimum. Yeah. So that's a challenge. Yeah. Yeah.
How are you encoding subsequences to then do the clustering?
Yeah, so there are a few different techniques that you can use for that. You can use autoencoders to kind of like reduce it down into some lower dimensional space. And then you can do your clustering based on the latent dimension inside of your variational autoencoders. Yeah, so there are a few different kind of techniques. This is definitely not a widely accepted approach to this problem. It's something that I like because I think it looks cool. But yeah, it's out there. People are trying this. It doesn't work incredibly well, at least in my experience. What works much better is actually just kind of like your change detection hypothesis testing approach and just assuming that your most recent data is what's relevant. But there's a variant on this which I'm going to talk about just now, which I actually prefer because it's much more robust to failures in the clustering algorithm. Okay, so let's move on to our next set of tricks. So basically the first three were basically how do we select data? Now, selecting data is actually kind of the same as saying how important is some data from some point in time. So data augmentation is either amplifying of the data you have if you don't have a lot, or it involves weighting certain patterns from your data more importantly than others. So data generation. One of the problems with using a pessimistic window selection strategy is that you often don't have enough data to train very complex models. So one of the strategies that people use is that as the window size grows, they use more and more complex models because you have more data for you to converge more complex models. And when you have a very small window size, you use a very, very simplistic model. Or what you do is something like boosting, where you have a whole bunch of like really weak classifiers which can converge on a small amount of data, and you combine them to kind of get the same effect. Another approach which we've been playing around with quite a lot of success is actually using generative models to generate more data from some subsequence. So let's say we're at window 2, we sample this window over here, and what we want to do is we want to train a very complex model on this data. So what we do is first we train a relatively simple generative model, and then we amplify the amount of data we have. So a very good test of whether or not your generative model is producing data which is similar to what you're actually sampling is to see whether or not the performance of the model trained only on generated data and your model trained only on your actual windows worth of data are equivalent or at least comparable. And we're finding some pretty good results here. So there are a few different types of generative models you could use. You could use variational autoencoders, conditional VAEs. You can use generative adversarial networks. There's a whole kind of branch of models that you can use in this space. This, I think, is actually quite similar to the idea of actually running a Monte Carlo simulation, except that you're not making the assumption that your time series are completely stochastic. So in a previous life, for the 3 years before I was at Numerical for 3 years, I was doing derivatives pricing at Old Mutual and other places. And there, you literally just assume that markets are random, you fit some sort of stochastic process, and you sample as much data as you can, and you price based on that. Now, the choice of stochastic process is about as complex as it gets, and I don't really like that. A much better way, or a more fundamental way, is to actually train a generative model. And the nice thing about this is that you don't necessarily get random data. You get noisy data from a generative model, but it can still have statistical characteristics which you can feed into a machine learning model and learn from. Yeah? Reinforcement learning. Did I write that? Sorry, where does it say that? Oh, yeah. Enough data to fix complex models, especially reinforcement learning agents. I don't remember writing that. Okay, so we have been playing around with reinforcement learning a lot, but we've actually been using it as a management technique for our online supervised learning algorithms. So for example, let's say you have some hyperparameter which is important. Maybe you can use your reinforcement learning algorithm to learn in what state you should make what selection of hyperparameter. Or another example is these models are all training at a particular frequency. So maybe what you should do is say, well, in what kind of state should I actually train, right? So maybe if you're in a very low volatility state, you can train less often because the market is not changing as much, so they're less likely to have a regime change. If you're in a high volatility environment and the probability of a regime change is increased, then actually the action that your reinforcement learner should make is to train your model more frequently. So that's where we're implementing RL. We have tried to implement RL as an actual predictive model. The problem with that is really just scaling, because we're not looking at one time series, we're looking at thousands and thousands of time series. On the input side, we're looking at about 19,000 time series, and on the outputs, maybe we're predicting 200-300. And it just doesn't scale very well, especially if your state space is very, very large. So we're actually using it on top as a way of managing all of our supervised learning algorithms. Yeah. Cool. So this is what I was talking about earlier, which is so we take our previous idea, which is where we cluster our time series, and we know that our clustering algorithm is almost certainly going to make mistakes. So what we do is, instead of just selecting data to train on based on the clusters, what we do is we assign some weight to patterns taken from that subsection of patterns, and basically we weight up based on the probability of it belonging to a particular cluster. So how that might look is like this. So instead of selecting just dog patterns, what we're going to do is we're going to say, we think that we're in a dog regime right now. So what we're going to do is we're going to sample all of the data we have, and we're going to upweight all the stuff which we think is from a dog regime, and we're going to downweight all the stuff which we think is not from a dog regime. So this is a little bit more robust to the performance of your clustering algorithm. And the reason why I prefer this is because your model always sees all the data, right? But you also bias it towards the current regime based on some probability. So if we are more likely to be in a dog regime now, we've actually upweighted those patterns when we were training the model, so it's going to hopefully perform better on those kinds of patterns going forward. So Stuart over here, that is his research topic. And I'm pushing him at the moment to get it done. But anyway, next idea. So this one I put, yeah.
Just clarity, what did you mean by upweighting the data?
Yeah, okay, so this is the idea of importance weighting or sample weighting. So you can kind of think, where's that chalk? Yeah. So we can kind of think of some patterns, right? And maybe this is like around 2008. And maybe these extremely low probability patterns don't occur very often. But if we're training our model, we're just going to pass this through, right? What we want to do is we want to say, hey, this pattern is very important, right? Or this pattern is likely to come from the regime that we're currently in, so this pattern is more important. So when we backpropagate the errors through the neural network, we basically we amplify errors from these kind of patterns, so it's more likely to adjust your network to deal with those kind of patterns. Yeah. Yeah. Sorry, can you speak up a bit?
Yeah, sorry. So I see a lot of these methods you're using might be a little bit more practical in terms of traditional asset classes where financial markets are a lot more stable. But I don't know if you have incorporated or tried it out in terms of more volatile markets where you have regime changes every 6 hours,
Yeah.
for example, in crypto assets and things
Yeah.
like that. So,
Yeah, we get that a lot. Yeah, we've tested it in, so I mean, we've played around with like some crypto data sets. That is another ballgame. I mean, you get like a regime change every 6 months. Okay, maybe not 6 hours, but like every few months, you definitely have a regime change. Commodities is very similar. So there you actually continuously having regime changes, and what we found is that the models by themselves with a fixed window size or a window size determined by change detection test and hypothesis testing almost never works because you never have enough data. But with some of these techniques, we found that it actually can kind of deal with these kind of uncertain, volatile environments and adapt to change much faster than a benchmark algorithm, which would just be trained on some recent window. Yeah.
So I get how you deciding that certain series of time are more important than others, like with the 2008
Yes.
example, as a human. But then how do you go assigning a value to that?
Yeah. So I mean, what you could do is you could use like your similarity or the probability of some pattern or some sequence of patterns belonging to a particular cluster as actually your weighting mechanism. So you can kind of think of it as like, let's say we have some time series clusters over here, and we have some over here, and we have some over here, and we have a pattern which sits right on the edge. What we can do is say, well, let's make this, I don't know, 30% weight, and we'll make this 60% weight, and we'll make everything from here 10% weight when we're training, because the probability of us being in this regime is much, much higher than us being in this regime, but we could also be in this regime, so let's include these patterns at a reasonable weight. Yeah, that kind of makes sense. We're busy testing a lot of these ideas to see if they work. A lot of the ideas don't necessarily work on all data sets, but yeah. Yeah. No, I'm a little bit confused. Okay. But yeah, I mean, basically, it's you can kind of think of it as basically just taking our time series, we're chopping it up into little contiguous bits. Maybe it's like 20 days at a time, a month at a time, 1 day forward. And what we're doing is we're clustering all of these, and we measure what regime they're most likely to belong to based on either measures of like how similar the probability distributions are or distances between those patterns. And when we identify that we're in a particular regime, what we do is we upweight samples which are drawn from that regime from the historical training data. Yeah, if that kind of makes sense. Yeah, you could do that. Yeah. Sorry, I misunderstood your question. Yeah, we've been playing around with like some probabilistic graphical models to kind of like model regime changes directly. So we can say, well, we're in this regime. What is the probability of us moving from this regime to this other one? We've been having some trouble with scaling. With those algorithms, generally, we don't have enough data to fit the structures which we're fitting our kind of like Bayesian models to. But yeah, I mean, you could definitely do something like that. Yeah.
Are you only sampling the same asset that you're trying to predict on, or are you doing it for like Bridgewater stuff, for example, correlated assets or assets from different countries?
Yeah, so generally that's where things get tricky. We are doing multivariate time series prediction. So when I say we sample, I mean we sample like whole batches of assets over periods of time. Generally, just for explanation purposes, we talk about the univariate setting, but it gets much, much more complex in the multivariate setting, which is actually what we do. Yeah. Cool. So I'm going to jump on to a few more tricks. So this, I don't have too much time, but this idea I kind of just came up with, and I don't know if it'll work. But one technique which people have used in time series in learning in time series environments is linear kind of sample weighting. So the most recent data points are more important than historical data points, okay? So this is kind of like a standard approach. So the idea is to basically do some sort of boosting where you train one model where you have an increasing importance on your samples, which are drawn most recently. And then what you do is you measure the error terms of those predictions on the training set. And what you can do is you can do a second round of boosting where you've weighted the patterns inversely to how difficult they were to sample. So the idea here is that stuff which is drawn from a different distribution to the recent patterns should be much harder to regress or to classify because it's actually drawn from a different distribution. But I don't want to spend too much time on this idea because I put it in there because I was like, hey, this is a cool idea. I'm going to pick another research student next year and give it to them. Model augmentation. So this is probably my favorite part of the slideshow. That's why I left it to last, and I don't want to skip anything. But error-based reinitialization. So this is critical, and we've actually had it throughout the slides all along. If you look at all of them, you say we transfer knowledge plus noise through time. So we have some model, and we actually have weights which we've trained. And what we want to do is we want to move to another point in time. We want to use those weights again, right? So we can kind of think of it as transferring knowledge from a previous point in time to another point in time. You can also think of it as basically a very optimistic initialization strategy. Now, the problem with that is that if you're in a local minima and the regime changes. So, for example, let's say this is our optimization surface over here in yellow for the previous regime. Now we've moved into a new regime and our error terms have increased, and this is where our model sits, right? So when we try to optimize it, we find that just because we're very unlucky, it's actually on a plateau. There's not enough information in there to actually generate gradients and to train our model. So you can kind of think of your model as getting stuck if you just transfer your weights from one point in time to another one. So the idea here is really just to reinitialize your neural network at each point in time that you want to train, based on or proportional to the amount of error term or the amount of noise which you've observed in the most recent period. So easy way to do that is to store your initial weights, and then what you do is you say, I scale my error terms to some value between -3 and 3, for example, and what I do, I cut it off and I say I'm going to basically create a new set of weights, which is where I was at the previous point in time, and it's somewhere between that and the noise component, and the noise component is actually my initial weights, because when we initialize a model, we initialize it with random weights. And what that allows for is that you move your model, you destroy information enough that it's actually able to pick up some gradients and optimize into a new local optima for your new regime. So if you don't do this, most of this stuff doesn't work. Basically, your model gets stuck and it never changes. Yeah. Any questions on that? Cool. Yeah, so this is basically just another reformulation of what a regime change is. It's basically a change in the optimality of your previous solution. Yeah. Another technique which we quite like is something called snapshot ensembling. I'm not sure if you guys have heard of it, but the problem with ensembling is that you have to train a whole bunch of models, right? But if we're continuously training our model through time, what we can do is actually cache previous versions of our models and load them up and weight their predictions proportional to how old they are. So this technically is not how it was used in the paper that I read. How they were doing it is they said, here's a data set. What we're going to do is we're going to optimize this model on this data set, and what we're going to do is we're going to basically save the weights as we go along, and literally through the stochastic gradient descent. And then what I'm going to do is I'm going to create an ensemble over the last 5 before it stopped with like an early stopping condition. So there, basically, you train one model, you get 5 for free. So it's a very, very efficient way to create ensembles. So this has worked in some cases, not in all cases. It really depends on how correlated the models are from the last 5 epochs when you're training. So basically, we just took this idea and we modified it for a time series setting. So what we do is we do a very greedy kind of training. We just train on a very small fixed window, which is obviously pessimistic, but we can train very, very quickly. Only simple models, but that's fine because we're going to ensemble. And what we do is we train for each period in time, and we create a checkpoint, basically, of the weights. We save the weights at each point in time, and then what we do is we create an ensemble at the top, which just takes your most recent model, weights its prediction highest. Maybe you have like an exponential decay on your predictions. So your most recent model is weighted at 1 times. Your previous model is weighted at 0.5 times on its prediction. And your previous model maybe gets a 0.25 weight on its prediction. So you can actually build an ensemble of predictions. And this is relatively robust to spurious regime changes. So let's say we observe something, we think we've had a regime change, but actually it was just noise in the markets and things kind of go back to normal. In that setting, maybe your most recent model has changed a lot, but your historical models are actually still retaining some of that historical information and you can capture that in your ensemble. So the reason why I like that is because train one model, get 5 for free. The only question is, how much should you weight each one of those models? Yeah. Cool. And this works really well if you're in a setting where you cannot run, like your data is not, your predictions are not happening on like a daily basis. Maybe you're doing it on a minute by minute basis. So maybe you've got some sort of like a watch which is tracking somebody's heartbeat, and what you want to do is you want to predict whether or not they're going to have a heart attack, which is actually a regime change in the rhythm of the heart. These kind of techniques are very computationally efficient because you just train one model continuously on a very small set of data, and you can just ensemble over the previous versions of that model. Okay, cool. So this is my favorite trick from the whole lot, and that's basically how you can approximate a Bayesian model using stochastic regularization techniques. This was a PhD thesis which came out in the last year or year and a half by a guy called Yaron Gell, and this is really, really cool. But basically the idea is that if I have trained my model with dropout, generally I don't do inference with dropout or with some other stochastic regularization technique. However, if I do inference with dropout and with that stochastic regularization technique, I can actually come up with a distribution of predictions from the model. So I kind of try to visualize this, which is I've trained my model, and then at inference time, what I do is I just randomly switch off different neurons. And what I end up with is a distribution of predictions taken through different paths through the neural network. So you can kind of think of a fully connected neural network with all of the neurons as being a neural network. If I randomly take one of those neurons out and throw it away, I mean, it's still a neural network, right? And if I've trained it with dropout, it should be robust to loss of information from any particular neuron or any particular input. So what I can do is it's not a true Bayesian model because you don't start off with a prior, but what you can end up with is a distribution of predictions. So this comes back to the question earlier about when your error terms are coming from, right? So if we're making predictions, our error term is our prediction from some previous point in time and whether or not we got it right or wrong. Like, that's our error. In this setting, what we can do is we can actually ask the model, how confident are you in this particular pattern or in your prediction given this particular pattern? And that's really interesting because then you start to get into an environment where maybe you've trained your model and these are your 3 regimes and you've got a pattern which is over here. And you have absolutely no idea what's going to happen, right? And you ask a model, hey, classify this pattern or regress from this pattern, and it comes up with wildly different answers at each point in time. So what you see there is that you get a much wider distribution of predictions from your pattern than you would if it's actually falling within historical data that you've trained. So yeah, this is basically a way that you can get an approximate Bayesian model from any point estimate model. It's extremely cheap, and uncertainty is a very, very important part of machine learning, which most people are not taking seriously enough, in my opinion. Cool. So basically out of time. Last thing, just a little bit of background about us. Current methodology. Essentially what we've done is we developed a general purpose multivariate time series prediction platform which allows us to easily create thousands of collaborative supervised online learning agents which collectively encode what I like to call a self-organizing investment strategy. And that self-organizing investment strategy basically adapts to change with the market using all of the tricks, which I've shown you today, plus some other ones. As of March 2018, so that's like recently, we have 1,200 deep learning algorithms in production, which are processing about 19,000 different time series. We want to be able to have about 50,000 different machine learning algorithms in production by the end of the year. The problem is that we are producing hundreds of gigs of data every single day/week at the moment. So if we scaled up to 50,000, we'd be producing 50 times that, and we don't really have the platform for that yet. So that's what we're working on at the moment. From a research/theoretical perspective, we've basically implemented almost every popular machine learning algorithm that's out there today, including ones which were only just introduced in NIPS 2017. So we're continuously doing improvement at this stage. We're adding new models, better data sets, and trying to scale up, like I mentioned. So the major focuses for us in terms of our research is deep reinforcement and active learning. So reinforcement learning, you guys will all be familiar with it because it's quite popular. Active learning is another strategy which most people don't know about, and that's where you're training your model, and your model actually tells you, hey, I'm uncertain about this kind of pattern. Maybe you arrive at that using variational inference, and you give your model more patterns like that sampled from historically or from some generator. And we're also very interested in deep learning interpretability research, because every investor we meet with says, why did you own this stock? Why did you sell that stock? And we don't actually know. So, and that's my talk. Yes. Yeah. So our models, we're actually predicting the regime change from our models' errors, right? So how well they're able to predict what's going to happen next. And what we're feeding into the model is a whole bunch of external outside information. So you can kind of think of the model as encoding some state of the world, and a regime change is when that world changes. And you can kind of think of when the model deteriorates, that's when you've encountered a regime change. So a bit of both. Yeah.
What's the rate of return that your company makes on its investment?
Well, yeah, we're actually looking very good right now. I cannot legally show historical returns or simulated numbers according to the FSB, but I can tell you they're very good, beautiful. The best lines you've ever seen in your life. But right now, our models have actually pulled out of the market. They're very uncertain. They've only been this uncertain at 7 points in history since 1995. So yeah, we're watching what's happening, sitting mostly in cash at this stage, but it's a very interesting test for our models. I mean, you couldn't ask for anything better, is that as you start your investment fund in October last year, is our first retail fund, the markets are going to shit, so you really get to test the ideas that you've kind of got in theory, yeah? Yeah. Yeah. So that's really just that's the art, eh? Yeah, we just pick. You know, maybe we pick based on like making sure we have enough data to kind of like do statistical tests. But yeah, there's still a lot of art involved in science. So that's the art. Yeah.
Any comments on point in time versus normal data sets? So,
like comments in terms of?
just the impact, because I mean, you can get quite easily sort of backtested results.
Oh, yes. Yeah. So we don't like backtest at all. We actually pretty much shun them, because I've never seen a bad backtest. You know, there's this thing, right? Never seen a bad simulation. So what we do is we actually do walk-forward optimizations through time. So if we have some model, we want to see how well it predicts or how well it would have performed, we only need to run that simulation once, because at each point in time or at some frequency through time, it's actually optimizing its own internal parameters to make predictions into the future. So you can run a simulation once and you get a pretty good idea of whether or not that model is able to learn how to adapt and change in that environment. But yeah, backtest. So this is a big problem in our industry, or in my industry, is that a lot of people will, let's say, come up with some simple strategy like a moving crossover strategy, which is basically I've got two moving averages of my stock like this, and when they cross over is when I'm going to buy and sell. Right? Now the problem is that they spin up an Excel spreadsheet. Honestly. You can tell I work on Amazon too much. They open an Excel spreadsheet and they try every possible moving average combination, and inevitably they find one which looks like this. and it's made an infinite amount of money. And the reason why is because of noise, randomness in the market. So people are constantly curve-fitting their results. So we believe that by continuously optimizing and making sure that our models are not able to overfit, using stochastic regularization techniques, using penalties on our weights, by ensembling and not putting all of our faith in one model, we can actually prevent that from happening. But of course, there is still some choice involved. I choose what models go into that 1,200. So yeah, there's always this risk. We're trying to minimize it. Yeah.